Hello and welcome to this second tutorial on GNU Octave on the Jokester designs. Today I'm going to extend the knowledge about matrices and arrays further. So the first thing I'm going to show you is a new generator function called magic, which basically generates an n into n magic square, where n is the number between parentheses, and this is going to give you a magic square of 3 into 3. So basically a magic square is a square where the sum along the columns and the rows and the diagonals are same. So moving on from that, I would like to declare another 3 by 3 matrix to be used along with this 7 8 9. Sorry, I put in an apostrophe there. So there are two types of multiplications possible between matrices. One is the standard multiplication, which you do, which is the standard matrix multiplication. The other is the element-wise multiplication. So A dot star B is going to give you an element-wise multiplication. The first element of A will be multiplied with this first element of B. This middle element will be multiplied with the middle element. So basically, each element in A will be multiplied with its corresponding counterpart in B. So here you go. 8 into 1 is 8, then you have 3 into 4 12, again sorry for that, 4 into 7 is 28, 72 is given by 9 into 8. So as you can see, these are element wise multiplications. Then I would like to declare a vector 1 12 36 35 45 98 78 76 13, and this is my vector. Now suppose I wanted to find the max element in this vector, so I would just put in a simple command max of v and would give me the maximum. Suppose I wanted to find the max value as well as the index of where it is stored, so I would just put in a command val comma ind is equal to max of v. That's going to give me the index as well as the value. It can be anything. You can write, instead of val comma ind, you can write value comma index, and you'd get the same. So it can be anything. You just need two variables as to where you want to store the value and the index. Suppose if I write a comma b is equal to max of v, so basically you get a and the max in the 90, max equal to 98, and the index in the second variable. The first variable stores the value of the maximum element, and the second variable stores the index. You can see 98 is stored in the sixth index. Moving on from that, I would like to show you, not I would try to use the max function on a matrix. So here I yield, I'll just print out a for your convenience. Here I yield the column wise maxima. So as you can see, 8 is the maximum for the first row, 9 for the second, and 7 for the third row. So basically when I implement the max function on a vector on a matrix, we get the column wise maxima. So in case this output is a vector, the output is stored in a vector itself. So in if I wanted to find out the maxima of the array, of the 2D array or the 2D matrix, what I would do is just do a max of max a, and that would, because max of a gives us a vector, and finding out the maximum in that vector would obviously yield the maximum of the entire matrix. So here you go, 9 is the maximum of this entire matrix. Then comes the sum function, where the sum of each element. But before that, I would like to show you the maximum, how to yield the column wise and the row wise maximum. You just saw the column wise maximum can be yielded by just doing a max of a, but there's another way of doing it. A comma square bracket open close followed by 1. 1 is the code for column wise, and 2 is the code for row wise. You would need it later on in the sum function also, and some other functions maybe. I'll be showing that to you. So basically 1 stands for column wise, and here you go, you have your column wise maxima. Just replacing 1 with 2 will give you the row wise maxima. Here you go. Now moving on from that, I would print the vector which I declared earlier and implement the sum function on v. Here you go, I put in a capital letter there, sum of v, and I get 394. That's the sum of this vector. Now if I again try implementing the sum function on my matrix, what would happen is I yield a column wise sum. As I mentioned before, that the sum of a magic square is same along its columns, rows, and diagonals, and that is being implemented here. And then if I wanted to find the, you know, total sum, again, these column wise sums are stored in a vector. Now, all I have to do is find out the sum of these of the three columns, sum of these three columns. So basically I'm going to do sum of a, and it's going to give me the sum of the entire matrix. If I wanted to sum up the columns in a different manner, I would put sum a comma 1. 1, as you remember, is the column wise sum. Sorry, it's a code for columns, and 2 would give me the row wise sum. Now if I wanted to find the, you know, the sum along the diagonals, what I would do is declare an identity matrix of dimensions 3 by 3. So basically I have I of a, which is a diagonal matrix, and now I would multiply it element wise and store it in a third matrix of type C. So a dot star I is going to give you, see, the diagonal elements, just the diagonal elements. So all I have to do is sum of C, and it's going to give me the sum of these diagonals. See, I get the sum of diagonal as 6 as 15. Now if I wanted to find all the elements which are greater than 7 and store it, means like, and you know, find their row and column position, all I needed to do is write something like rows comma columns. Remember to write your rows first and the columns later, because that's the order in which they give you. And then equal to find a greater than equal to, say, maybe 3. Okay, and it's going to list all the columns and rows. So the first one is in case, let me print out a once. The first one is in row 1 and column 1, and that's 8. Then the second one is in 2 comma 1. So 2 comma 1 is basically the second row. First element is 3, greater than equal to, remember. The third one is in 3 comma 1, again in the third row, first element. And similarly you have all the elements which are greater than equal to 3 listed out in rows, their rows and columns listed out. So if I wanted to, suppose I have my C, if I wanted to flip this C, what I would use is something called flip UD, and it's going to sit along the center. It's not going to flip it along the diagonals, it's going to flip it along the center. You see, the major diagonal becomes the minor diagonal, and the minor diagonal becomes the major diagonal. And there is another function which I would like to show you, that's the PINB function, which gives you the inverse of your matrix. So there you go, that's the inverse of your matrix. Okay, that's all for the second tutorial. This was just a basic extension of the first tutorial on certain points which I might have missed out, and I wanted to do it badly. And maybe because that was just an introductory tutorial, I didn't feel that that could have been this could have been included there. So please do like, share, and comment on my videos. Do subscribe to my channel. Signing out from the Jokester Designs.